I knew that basically a continuous process was basically what a super, super efficient process looked like. And a continuous process is essentially is pretty much what it sounds like, is basically you have, your series of production steps that like make whatever it is that you're making and transform, your inputs, your raw materials and energy to whatever, widget that you're trying to produce or good that you're trying to produce. And a continuous flow process basically does all those steps continuously, one after the other immediately with no waiting or downtime or failures.
I'm your host, Ritwan, author of the book Data Impact. Welcome to SLASOG Leaders or Readers. Here I speak with outstanding operators and seminal thinkers to unpack first principles system rethink for data-driven value creation. Hi, Brian. Welcome to SLASOG Leaders or Readers. I've been reading and thinking about your book for several weeks now, The Origins of Efficiency, and I'm really excited about speaking with you about it. But to kick it off, if someone's not heard of you, why should they listen to this conversation?
Sure. So yeah, my background is actually in the construction industry. I worked for about 15 years as a structural engineer, designing buildings and apartment complexes and water treatment plants and things like that. And then in 2018, I went to work for this construction startup called Katera that promised to just revolutionize the construction industry and make it so much more efficient and change the way we built buildings, which was not that different from, at the time, not that different how we built buildings, 100 years ago or something like that. And at the time, I was very excited to join this company. I thought they had the exact right idea, and, the industry was extremely inefficient, and we were doing things that, ways of they're very old fashioned ways of doing things that seemed like they could be done so much better. So I went, I joined this company with this idea like, oh, we're going to change this industry. We're going to make it so much more efficient. And it just didn't work out at all. They raised a very, very large amount of venture capital, like $2 or $3 billion worth of funding, and then built all these factories and then burned through the funding in a relatively short amount of time. And then declared bankruptcy after COVID. And then in the aftermath of that, I kind of wanted to understand why it had all gone so wrong beyond just, whatever operational missteps that they have made or, bad business decisions. I kind of came to believe that their sort of thesis, which was essentially that if you just move these construction processes into a factory, then your process will get much more efficient and you can build your buildings much cheaper and you can be the low cost producer, right? You can be the Henry Ford of housing, doing the same thing for housing or for construction that Henry Ford did for car manufacturing, which was like change it from this craft manual process to like this factory high efficiency, mass production type process. And it just, I came to believe that idea just wasn't quite correct. There was something about construction that made it so you couldn't just move stuff into a factory and getting these all these efficiency improvements, because many other people other than Katera had tried basically the same thing and not really succeeded. You kind of see these attempts going back many decades, just kind of all around the world. And so I kind of want to understand why that was true and what about the construction industry made it so difficult to improve and, make it more efficient over time, and have the cost of building things fall over time, which it basically almost never does. And it kind of, I kind of got the idea that we clearly in some level didn't really understand what it took to make some process more efficient, because if we did understand it, as a civilization, if we understood it really well, we wouldn't keep making these bets on construction that didn't pan out, that, these factory-based construction processes that failed to sort of achieve what their goals were. So I wanted to sort of research and understand what specifically it took to make some process get more efficient over time, and when you could get these efficiency improvements and when they were blocked. And so that's kind of the origin of the book. And so the book is sort of based in my experience in the construction industry, and when it is very hard to sort of make these efficiency improvements happen, and what specifically needs to be true for them to sort of accumulate.
Yeah, and I can just vouch for the fact that this is such a first principles look at efficiency in production. I've never like that's been a blind spot personally for me, and I've been looking for the right book that helps me understand efficiency in production, and I think your book just nails it, and it nails it in such a nice way. And it's cool to see that you went from construction and sort of looked at manufacturing of other things, because you speak about penicillin and light bulbs and a whole range of other common products, which kind of builds actually to the next question, which is, what's your fundamental disagreement with the course? As an operator, I think you were involved in sort of this very ambitious attempt, and then you researched why it didn't work out, or what the challenges were with construction. So, like, why do you think this book needed to exist, and sort of what is that disagreement? Like, what was missing in the status quo, or what was wrong, or what's the wrong impression that people had?
Yeah, that's a interesting question. I'm not sure I would characterize myself as having some sort of fundamental disagreement with the status quo. A lot of kind of what my work is like going through and researching existing history and kind of summarizing things and coalescing things in a way that like ties a bunch of like different kind of ideas and concepts and examples together. One thing that made it easier to kind of write the book was I had a reasonably good idea of like what an efficient process looked like, right? Like I knew, mass production stuff made stuff really cheap. I knew stuff like, the innovations that Toyota had introduced had like made, improvements even more. I knew what generally at a sort of a high level, what, an efficient process looked like. So that was made it easy to have like a sort of a star to some extent. Like when I was sort of trying to like break it down into sort of its individual pieces, I kind of knew it's like, okay, when I put this back together and have this like idea of what a process needs to get more efficient, it should look like this thing that I already know is pretty efficient. And if it doesn't look like that, that I've gone wrong somewhere. And a lot of kind of my work beyond this book is like that. It's like, breaking something down and dive and trying to sort of research as deeply as I can some specific topic where I already kind of know what it looks like, but just going deeper on sort of the details about it. With this specifically, I think just no one had tried to sort of just stitch all these different ideas together before, and there was all these sort of like very like kind of narrowish ideas of efficiency, like we know mass production makes stuff cheaper. And there's all these sort of industrial improvement systems, Toyota production system and lean manufacturing and Six Sigma and all these sorts of things. But they're all kind of a little bit narrow and focused on these a certain specific things that you can do on a factory floor or something like that. And no one had really tried to sort of just stitch all these things together in sort of a more coherent whole, and being able to sort of apply it to sort of at a higher level of abstraction to sort of like industries and processes more broadly. And so that's kind of, for some reason, people had not really tried to do that. And when people were trying to sort of improve these processes and things like construction and stuff like that, they were kind of going on these like more narrow kind of ideas, basically like, we just, mass production bring stuff into factories that make stuff cheaper. And so there was just something missing because no one had tried to like stitch these kind of somewhat disparate concepts into some sort of a broader whole. But a very large amount of what I was doing was just basically taking a lot of these existing fairly well-fleshed ideas and seeing how you could kind of fit them together into a little bit something broader sort of concept. But it's very much a work of synthesis of sort of existing things.
Yeah, and I think trained as a mathematician, I think that's why it really resonated, is because it almost feels like you're building an axiomatic theory of efficiency. And of course, it's not like in math, right? This is the real world, but it brings that nice first principle structure. Because you spoke about this process of, everyone knows mass production, and that was your guiding star. In the process of researching and writing the book, did you discover something that kind of surprised you, shook you, something that you went like, oh, I thought I knew this, but actually, no, it's very different? Were there such moments, or were there other moments where you said, I knew this, but now I know it in a completely different or crazy way that I didn't think was true?
I was a little surprised at how old some of these ideas that sometimes seem quite modern are. And you see the same thing in like construction more generally. Like every 10 or 20 years, it seems like someone comes up like, oh, if I just build these buildings and factories, it'll be so much more efficient, and I can just like, my costs will be so much lower, and I can transform the industry. Everybody has this like light bulb moment. And that idea goes back like many, many decades to like the early 20th century in some ways. People were kind of trying this basic idea. I've sort of said before that for any given like clever idea in the construction industry that's not predicated on some like radically new technology or something, but sometimes even that, somebody has probably already tried to do it several decades ago and probably went bankrupt trying it. So any existing idea in construction kind of has like a very long history if you can dig into it a little bit. And I kind of found that with sort of a lot of these concepts in the book. So, one example is like, Toyota production system and lean manufacturing is this sort of set of ideas that came out of Toyota starting in like the, after World War II, sort of 1960s, 1970s, where they sort of refined this like method of manufacturing that was based on what seemed like very novel ideas, which is kind of these ideas that like inventories are bad, wasteful movements, you should minimize waste, which means like minimizing the travel time. We're not having a lot of like wasted movement of different parts and stuff like that. But then if you go back into the history of manufacturing and look at like things like guides to like mass production methods or like what manufacturers were doing even as far back as like the 19th century or earlier, they understood a lot of these basic ideas that, oh, if something is like you're having a thing move around a lot in your factory, that is like a lot of wasteful movement that you should try to kind of minimize. A lot of the basic ideas and stuff like the Toyota production system and lean manufacturing show up in things like scientific management, which came the early 20th century. So that was one thing that surprised me, was how like similar to how I was talking before about how there was lots of conceptions of these like efficiency, but they're kind of like narrow and focus on a particular thing. I kind of saw like these same ideas pop up over and over and over again in these like specific applications and specific like conceptions of it. And so it ended up being quite rewarding for me to be able to like, have this idea and say, okay, and here's where it shows up in this thing, and here's where it shows up in this thing, and here's where it shows up in this thing, which kind of like, again, strengthened my idea that I was kind of on the right track of how I was thinking about things.
Nice. Let's just grab the bull by the horns now. I think you came up so many times, this idea of, okay, we can produce something in the factory as far as construction is concerned. Why doesn't it work? Like and like in its most recent iteration, but also going back decades, perhaps even centuries, what's the crux? Like, why is this now working? And what's the core? What's the knot there? Like, what needs to be untied if at all this were to work, or is it really impossible?
Yeah, so I would say the basic thesis of the book is that, when you want to improve some process and make it more efficient, as I sort of talk about it in the book, means like, using less resources, fewer inputs to make something and basically lower the cost of production. I kind of use it synonymously with making stuff cheaper in the book. And there are kind of different ways you could think about that. That's not necessarily the one true way of thinking about efficiency, but that's kind of the path that I took in the book. But anyway, there are like, specific ways that you can kind of intervene in a production process to kind of make it more efficient, to reduce the amount of resources that it takes. And that if you can do those things, you can make your process more efficient, you can make it cheaper, and it's great. But if those paths that you have are like blocked, then it's just very hard, if not impossible, to sort of make your process more efficient. And kind of what you see is that all these like strategies for making a process more efficient, they're all very, very hard to do in the construction industry as sort of one example. And I'm sure we'll go through all the different sort of strategies that you have. But just to start it off, one thing I talk about quite a bit in the book is economies of scale. These are historically been a pretty important way that things have gotten cheaper over time. You make more of something and, you make it for cheaper, basically produce something in very, very large volumes. You can make it more inexpensively than if you produced it in small volumes. And it's kind of hard to capture these economies of scale in construction, kind of for a variety of reasons. Just the market is not that big. Even like very big markets, you're not making really stuff, the identical things in really, really, really huge volumes. You can't the buildings are so big that if you make stuff in a factory, you can't transport it very far because it's just so expensive to like move these things around. So so an individual factory is kind of limited in what it can produce like within a certain driving distance. And so an individual factory can't necessarily have enormous economies of scale where it makes, hundreds of thousands of identical buildings in it. And so, that's kind of one example. But if you look at all the sort of other paths of efficiency improvement, they're all kind of difficult to achieve in construction.
I think there's one example that stood out, which was, I think, when they started using metal rods in construction in India, and they had to use smaller ones because the American rods were transported by trucks. But I think the ones initially on the Indian subcontinent in the 60s were using push carts. And so you just couldn't carry that big and heavy a metal rod. And yeah, I mean, now that you've said it, let's go into your core thesis, right? In terms of, every production system has 5 steps, right? So you say the 5 steps are, there is some kind of transformation method, right? So the logic that takes inputs and converts it into an output. And it's usually obviously a physical mechanism for industrial products. Perhaps, in financial services, it might be capital. I was just thinking about equivalents for insurance and other products. Then it's not necessarily physical, but it's still a sort of a fixed, cost of replication, right? You have a production rate, the speed at which these steps can operate. And I think you say, okay, there's some kind of notion of the unit of time, and that's where time really plays a role. You have the costs, of course, of the inputs and the outputs. And then you speak about buffer sizes and work in progress. And finally, you speak about variability and yield. So my first question was this idea of variability and yield. I felt I understand both these concepts separately. So variability is, when things are kind of volatile, swinging around. Yield is sort of, like your ROI. Why are these two together? And like, what does it mean? And then kind of to wrap it up, is this list really exhaustive? Why do you think it's exhaustive? Like, how did you mentally, how do you juggle these balls and be like, okay, this is it, these are the 5 sort of axioms?
Yeah. So with to talk yield, this is like I think a term of like art in the manufacturing world. It's like a little bit different than how it's used in finance. Yield just means like the percent of, the percent of output you got that was good out of the theoretical amount that you could get. So if you, have like 100 inputs and your process does it correctly on 99 of them, and one of them it screws up and you have to toss it, that's a yield of 99%. And that's
so is that total material minus losses, like minus material lost or something like
basically, yeah. It's like it's like the, the percentage of good output based on, compared to like what the maximum possible output was based on what your inputs were. So it does, the number of it's based on like how much you had to like toss or rework basically. So yeah, that's just a term of our in manufacturing. And yeah, how that's coupled with variability is just the more variable that your process is, the more that sometimes is going to spit out something that is outside of tolerance or breaks. And so the more variability you have, the lower your sort of yield of your process is going to be. And so, yeah, regarding the sort of 5 steps, I kind of, it actually took a while to sort of conceive of the book in those terms. Initially, when I first started writing the book, I hadn't sort of thought about it in that way. And I was sort of writing all these chapters that weren't turning out very well because I didn't have this like strong guiding structure of the book that ties it together. So I kept having to write all these chapters and like throwing them out because they weren't any good. And then so I just kept thinking about these ideas, like what are and I was reading all these things about like different ways that people had historically improved like production processes. And I just try to kind of like, that's just a standard way that when I pursue some topic and research it, is I try to, break it into like specific chunks, and each one of which is like easier to sort of manage and get your head around. And so I just started to try to like think of like terms of like, here's all these different strategies that people are using. Can I like conceptualize them in just like a discrete set of chunks? And this like, this sort of 5, factor thing is basically what I came up with. And, I think it's ended up being correct because every kind of example that I, researched and looked through, I could sort of categorize it in one of these things. I asked like sort of a collection of other manufacturing people that I was associated with, if they even, just basically giving them this list, like, hey, if you have any improvement, is there any sort of, one of these boxes that it can't fall into? And they said, no, that kind of pretty much covers everything. And part of it is that kind of when you're breaking something down, when you're trying to have like, have this big collection of things, I want to sort of categorize it in like, several different ways. You want it to like sort of be like, have full coverage of like every possible thing. Some of your categories end up being a little bit broad and a little bit catch-all. So they can like, your categorization can accommodate whatever it is that, whatever item might want to sort of fall into it. And that's kind of true here. Some of these categories are like quite broad. So like any sort of, any sort of like possible efficiency improvement can like be categorized in there a little bit. So like inputs and outputs, that's a pretty broad category, right? You can often, it's very easy to sort of think of any given thing in terms of like inputs and outputs and fit it into this category. And again, the transformation step also, again, that's like a very broad category that can sort of, accommodate sort of a lot of different ideas of what it, how sort of an improvement, efficiency improvement might happen. So yeah, it's sort of a combination. How I came up with this, just sort of a combination of like just, doing research and reading a lot about different sort of efficiency improvements, and then thinking based on that, thinking through sort of a breakdown that could like was sufficiently flexible to sort of accommodate the sort of different improvements that I saw.
Yeah, I think, and it's quite convincing, and it's what comes out of these 5 steps, right? And I think that seems to be the core thesis in terms of how efficiency is driven. Like once you have these 5 modules, these 5 building blocks, is you argue for continuous flow processes. And so, what are these continuous flow processes and why are they so important for efficiency? And thinking about just the words continuous flow made me think about things like reducing friction when, doing some kind of mechanical engineering, or the idea in fluid dynamics, right, of this flow where, there is no turbulence. So how much do these ideas from physics also play into this? And yeah, why are continuous flow processes so critical for these 5 steps in efficiency?
Yeah, this is sort of another interesting synergy that came about when I was writing the book. Because when I started, I knew that basically a continuous process was basically what a super, super efficient process looked like. And a continuous process is essentially is pretty much what it sounds like. Is basically you have, your series of production steps that like make whatever it is that you're making and transform, your inputs, your raw materials and energy to whatever, widget that you're trying to produce, or good that you're trying to produce. And a continuous flow process basically does all those steps continuously, one after the other, immediately, with no waiting or, downtime or failures. It just does it smoothly and swiftly and just continuously. Is sort of kind of, the sort of whole process kind of looks like one big individual machine, that everything is like moving smoothly through that. And so, mass production, or the assembly line where stuff just moves along this line is like continuously transformed. Is sort of an example of something that, approaches, maybe not quite 100% achieves, but approaches a continuous flow process. And I kind of knew that was what these really, really efficient processes looked like, because I knew of many examples of ones that like, could produce things at like very, 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 very high volumes and very, very inexpensively. And so it was a sort of an interesting thing that I stumbled across, where I already knew that this continuous flow process was what a super, super efficient process looked like. And then when I had all these factors, I looked like, oh, wait, if you like push these factors to the maximum, if you try to make your scale as high as possible, if you have like a really, good transformation method, if you have, as cheap inputs as possible, if you have like almost no buffers and no variability in your process, you kind of get something that looks like a continuous flow process. An indication that I was basically on the right track as to how I was thinking about this, because again, these ideas pointed to something that I already knew kind of basically had to be true at some extent. The reason that the sort of idea that a continuous flow process is extremely, extremely efficient is kind of simple. Because if you think just from first, from basically as to how would you, for any given process, how would you do it most efficiently, you would sort of come up with the idea like, okay, I would just do each step that the process needed to do immediately, one after the other, and not do anything else, and just do those steps, one after the other until the thing was done. It basically just means that you're doing every single step that you need to do as quickly as possible without any sort of waste or downtime between them. If you think about like writing a long document, the very fastest and most efficient way to do it would be to just type each letter one after the other as quickly as possible without sort of any waiting to think about what it is that you need to write, or, the ideas that you need to sort of come up with. If you can just, put one letter in front of the other, or one letter after the other, one at a time, continuously, you will complete your document very, very quickly. And so the continuous flow process is basically just this idea. It's just do all the steps that you need to do to make your thing one after the other immediately without sort of any waiting or redoing or failures of the process. And so that's kind of how I kind of think about why these efficient continuous flow processes are so efficient. In terms of physics, I'm not a physicist, so I couldn't, speak to the sort of deep relationship there, but you're definitely right to the idea of like, yeah, it's like, removing friction from this process is really key. There is sort of an interesting parallel in mechanical engineering to these idea of a continuous flow processes where if you're making a machine to do something, oftentimes the best and most efficient way to sort of make that machine is if you can have some sort of component that like rotates and just spins over and over again, because this has like these same ideas of continuous flow processes. Or if you're not starting and stopping, but just like spinning continuously, you can make your machine a little bit more robust and more efficient and work a little bit better. This is why, jet engines were in some ways a lot better than the reciprocating engines that they replaced, because with a jet engine, you basically just have this one big moving part, and a reciprocating engine has these parts that go, pistons that go back and forth. And in some ways, those that sort of, that one big spinning part option makes a sort of a better, more elegant, better working machine.
Which kind of leads me to, I think, two very common things that everyone seems to know and that you also referred to, which was Ford and the assembly line, and then several decades later, the Toyota production system. So why are these two milestones so important and well known? And what happened in between? Why are they important? And what did the assembly line and Ford radically change? And given that the assembly line already existed, like why is Toyota production system, like why did it have the impact that it had?
Yeah, so Ford was basically the transition from craft-based car manufacturing, which was like stuff was like built in place by, skilled manual labor, like one part at a time. That would have a cart up on, blocks or, a lift or whatever, and, just bring the parts over and put them together one piece at a time, just fixed in place. And Ford's big realization, again, going back to the idea that a lot of these ideas of, efficiency improvements that seem maybe somewhat new are really stretched back quite far. And Ford kind of, realized that if you just kept the person in one place and moved the car along a line and brought the work to the worker, that would have a lot less wasted movement. The worker wouldn't be walking back and forth to have to get things. You could keep, and if you did that and then further subdivided the jobs that the worker was going to do, they could just do this one task over and over again, and that would be much faster. And this is just this is an insight that goes back to Adam Smith, right, in the pin factory, back to the sort of 18th century. So what was notable about Ford and the sort of assembly line wasn't this idea that like, oh, we structure this thing in this like, flow type process where the goods move along this line, and you have this sort of, again, like something approaching like a continuous transformation of parts. What was notable wasn't that he created that idea, because you had like really efficient, continuous type processes that existed before that, but they were for like much simpler things. They were either for like bulk materials, like grain or stuff like that, or they for like really simple manufactured goods, like cigarettes or matches or stuff like that. So it was so notable and important about Ford and the assembly line was this is when the first time that you had like this sort of continuous flow type process with like a very, very large, complex manufactured good with like hundreds or thousands of parts in it. prior to this, you really had these sort of assembly line, these sort of continuous flow type processes with, they only existed like much, much simpler manufactured goods. And so the idea with Ford is like, oh, you can have this like really efficient continuous flow type process. And of course they didn't think of it in these terms, right? But this is how you can, looking back, this is how you can characterize it. You can have, the idea with Ford is that you can have these like continuous flow type processes with basically any like complex manufactured good. And that was what was so transformative. And yeah, it sort of made it possible to have these like quite high quality cars for like very, very inexpensive. That was what the big deal about Ford was. You could have this like really, really good car, as good or better than anything else on the road, for much, much, much cheaper than anybody else could produce it, until they adopted kind of these similar methods that Ford did. And so, yeah, you have Ford develop these methods in like the early 20th century up through like the 1920s. And then kind of around then, you kind of Ford had like just dominated the field for like quite a bit of time using this technology that he invented, or like, not he, but the company kind of invented. Many, many people contributed to it. But then other kind of manufacturers eventually figured out how to, adapt these, and develop there's like similar ideas. And so companies like General Motors kind of, and Dodge kind of started being more and more competitive with Ford. And then for a while, Ford was like stuck in this very like, idea that we just need to kind of keep making the Model T and just kind of keep reducing the cost. And that worked for a very, very long time. But eventually the sort of market changed. People wanted sort of better car, new and different cars. General Motors kind of realized that you could, cars were in some sense like, a stylistic good, or, a good where like, fashion was a kind of what people were buying when they were purchasing it. And they came up with the idea of like, oh, we're going to change the model every year and have like new interesting models that come out, on a regular cadence. And by introducing that, they were able to kind of like take big market share away from Ford. And Henry Ford himself actually came close to like just driving the company into the ground, because he kind of was just very locked in sort of the original idea of what had made the company kind of so successful. And then kind of he, eventually the company passed from him to sort of other people, and they kind of entered into sort of this three-way competition between Ford and General Motors and Dodge. And those became, the big three U.S. car manufacturers. And then that, that sort of was the status quo in the U.S., through World War II, roughly. And then the whole, with Toyota, the sort of how that evolved, which was like, after the war, that they were sort of producing cars. They wanted to sort of better understand how to sort of make these things more efficiently. Some Toyota people, I don't remember exactly who went, but they visited the U.S. and they went and visited these like Ford plants and these very big, what's this facility called, the Rouge, which is this huge, massive Ford manufacturing facility in Michigan. And they sort of saw what they were doing to sort of make these cars, in really huge volumes. And they were very impressed with like the system that they had, but they also thought that it couldn't really work as is for the Japanese market, because the Japanese car market was much, much, much smaller, and it couldn't, and it also, it was small, and it also like demanded a kind of a lot of variety of cars and trucks that it was producing. And so the technology of Ford and all these other, U.S. car manufacturers was basically predicated on producing stuff in really, really huge volumes. And the Toyota just thought they could produce, the market didn't exist for them to make stuff in those large volumes. And so they wanted to sort of think a way that they could adapt these mass production type methods to sort of their needs, which were like much smaller and like a larger variety of output. And so that was kind of the ideas that became the Toyota production system, and which in turn evolved into sort of lean manufacturing. And these ideas, which has been like, you should, minimize the amount of inventory and work in process that is accumulating in your operation, right? These sort of American car manufacturers, they often had like every given station for it was, producing some part. It might have like a huge stack of inventory of parts waiting to be processed. And the Toyota folks thought that was like very wasteful. If we work to sort of improve the reliability of our operations, and so, one step smoothly goes into another, we won't have to have these big, huge stacks of parts that accumulate, and we'll have less waste and stuff like that. And they focused a lot on like not having like really long movement distances for parts, having, stuff so went from one machine to like another machine very easily, which is also an idea Ford had, but it's sort of at some point been lost as sort of the mass production ideas continued to develop in America. So and they sort of did all these other things. I talk about it in the book, but basically the ideas behind Toyota production system was that, taking these ideas of mass production and adapting it to a market where you could sort of, adapting it to a market where output was smaller and variety was a little bit higher. And then those basic ideas kind of have spread around the world. It turns out you can sort of take these basic concepts and apply them to a lot of different manufacturing operations. And that was what became sort of what's now known as lean manufacturing, which of course is very widely adopted, very widely used in all sorts of different manufacturing operations.
So in broad brushstrokes, right, they're taking the scale of the Ford approach, and then they're kind of batching it up into smaller batches, increasing adaptability, right? And also kind of removing the friction that such a batching would include.
Yeah, they're making it. They're trying to dial what they're producing to like the needs of the market, producing at a rate that is is basically how much they're able to sell this, not just trying to make it in like really huge operations, and trying to sort of make it easy to sort of change what they're making so they can like flexibly adapt if the market shifts or they need to make something else, they can change what they're making. So there's these ideas called a single minute exchange of die, which is that a die is like a big piece of metal that goes in like a that is used to like stamp out a part in a particular shape. And historically, die changes if you wanted to change out your die, so your press or whatever would make a different part. Those die changes took a very, very long time to do. And so what they, historically what car manufacturers did was they would like set up a machine with a particular die and then just run it as long as they could, because it was so time consuming and wasteful that they thought to change out these dies. And this is one of the big sort of innovations in that Toyota sort of adopted, which is like, well, if you just figure out how to do these die changes a lot quicker, we can sort of switch them out and change up what we're making and not have this like really long downtime. We can just change it out really, really quickly shift to what we're making. And so that was this idea is like single minute exchange of die, changing out, taking a die that maybe used to take hours to change and figuring out ways to change it in a single minute, and sort of give their production system a lot more flexibility, the ability to handle, a variety of things in a ways that sort of the more rigid American mass production methods couldn't quite handle. So yeah, it was like taking these ideas of mass production and adopting them to sort of be more flexible, basically.
This makes me think very much of pit stops and changing the tires in Formula One. And to sort of take a step back and just ask you like a deeper, broader question, which is, you can make the engine faster in the car, or you can find ways to do your pit stop faster. At the end, it's still, as far as winning the race is concerned, I think the contribution, if you shave off 30 seconds with the speed of the car, or you shave off 30 seconds from the pit stop, no one cares. Right? At the end, it's about like your car has gotten 30 seconds, like you're winning the race, you're completing the race 30 seconds faster, and that's what matters to winning. So to what extent do you think technology is a driver? To what extent is it about how that technology gets used and sort of built in by humans? And are those like, what's the relationship between these two? And, how do you get this, like, how do you speed up this whole thing? Both the new technology and then, how you leverage that technology.
Yeah, that's a really interesting question. And I wish that was something I wish I understood better. It's like, what for these different like factors, what is their like relative importance? And that's something that I wish I'd been able to sort of dive deeper on. But I was not able to like, this is like 25%, and this is 10%, and this is 5%. Ultimately, I think like the improving technology is kind of ultimately one of the most important, because the technology that you have is ultimately what sort of sets the sort of cap or limit on like how efficiently you can sort of produce something. And so if you want to exceed that cap, exceed that ceiling and do something, faster with fewer resources, ultimately you're going to be constrained by your technology. So ultimately you need to find more efficient, ways of doing that, or things that like allow things to be done faster. So I talk about, one example I use in the book is like making nails and the sort of technology, nails that, use to, nail boards together, and the technology used for like how the technology for making those changed over time. And for many hundreds, thousands of years, the way to make nails was just they were hand forged, which you had like a big piece of iron and you would like cut it off and just hammer it into shape, basically. And if that's your nail technology, there's only like so efficient that you can make that, right? Like you can have all the scale in the world, you can have all the like, variability reduction, in the world, and it's still going to be like nails are still going to be expensive if they're like tied to this process where it's like made by hand by some sort of expensive labor, right? There's only so fast that a person can work, right? There's only so like precise that they can work. So all these, so I talk about this in the book, but all the sort of other factors of production, all these sort of like 5 that I talk about, they're ultimately governed by like what your production method is. And so ultimately to like sort of accumulate these, continue to sort of make these efficiency improvements, you ultimately need to sort of make better technology or introduce new and better technical ways of doing things. So I think changing technology is like ultimately kind of sets the pace for these things, or ultimately determines like how efficient that you can make it. But sort of within a given technological paradigm, there's also a lot of possibility of improvement, for introducing sort of, these other types of process improvement. And sort of after that, I think scale is kind of the next most important one. That's just something that we see over and over again, just how important it is to look, being able to operate as large a scale as possible. And again, this is an idea that goes back to Adam Smith, right? If you can sort of have your division of labor and sort of make, you can make your pins or whatever much more cheaply than you can if you're sort of each worker is making like one pin from start to finish. But that division of labor is predicated on having like a very large, market to sell these pins into and be able to operate like at a very large scale. And in sort of The Wealth of Nations, Smith talks about 10 workers or whatever in the time it if they're set up in this division of labor, and so each one is doing like specific step, a worker can, these workers can make 18,000 pins or whatever in the time that it would take. They could make 1,000 or something if they were making them each individually, or some much smaller number. I forget the specifics. But if you're making 18,000 pins, that's predicated on like having a market you can sell 18,000 pins into. And so economies of scale, I think, have historically been like quite important. That was another important thing with Ford. He was able to sort of make these extreme like efficiency improvements and make the Model T really, really inexpensively. But in doing so, he had to make it in like really, really large volumes. And though a lot of the improvements that he introduced would not have been possible without the very, very large volumes of cars that he was selling. But I think those two are quite important in sort of, if we're doing some sort of conception of the relative importance.
Yeah, and with an existing technology, how do you kind of, how do you squeeze the lemon harder, right? How do you get more juice out of that? I think there's this fascinating story, which I just couldn't help smiling all day when I read it. It was about how this guy in I think it was in England, was it Earl Buckingham 1942 on manufacturing, where they have these spinning bobbins and they're figuring out how a certain thread making, like the threads kept breaking in the thread making process, and there's one guy who just somehow cracked it, and like his stuff always kept working. And then they try to observe. He was doing the exact, like everyone was doing the exact same thing in the factory, but somehow this guy was able to nail it, and everyone else, their threads kept breaking with the bobbins. And then, finally they called him over. They tried to figure out, hey, what's going on? And, initially he refused. At the end, they said, okay, we will pay you whatever you want, but tell us how you make it work. And he asked for a pint of beer every day until he dies. So I was like, okay, that's a cool ask. And then they said, okay, now tell us how you get the damn thing to work. And he said, oh, just chalk your bobbins. And it reminded me what a friend's dad from school shared, who used to work in the early days in telecom. They had these towers that ran into technical glitches, and all the engineers were, banging their heads against the wall trying to figure out what to do. And there was this older engineer. He would send them all out of the control room for like for like 10, 15 minutes. And then when they would come back, everything was working again. And they just kept thinking, what the hell is this guy doing? And why is he not sharing it with us? And then I think at some point they confronted him, or he was about to retire, or they came this point where they had to know what was going on. And he just said, oh, I just reboot all the systems. So, which brings us to this idea of tacit knowledge. I think this is so important because a lot of people, like, especially now in my field, there is this chutzpah, this feeling, hey, we have all this data and all this internal, call logs and documents, and we just throw it all into an LLM, and then it's going to tell us, we'll be omniscient. There's a bit of that dream, illusion, hope. And I think what comes across in your book and research is this idea of tacit knowledge, right? There is just so much like chalk the bobbins or stuff like that. It's not, it's not even documented. It's in people's minds. It's some craftsmanship. These are not everything kind of, is sort of machine readable in that sense. And talk us through that, like what is that, like the importance, the criticality of tacit knowledge, and how every time you think you've taken tacit knowledge and standardized it, it leads to new tacit knowledge by definition, because that's progress.
Yeah. And yeah, tacit knowledge, like this idea that like there's a lot of like, knowledge of how something works or how to sort of get something to function is like not written down anywhere, or sort of not legible or not accessible. Which, a lot of it is just like, yeah, in the heads of these workers that are like doing sort of the process that you're trying to do. And so, yeah, having all this, this tacit knowledge is sort of, you need this to sort of make these things function, but it makes it very difficult to sort of make these production processes portable, because so much of it introduce like some new operation and some new location, because so much of it is just like, yeah, existing in sort of these workers' heads and sort of hard to sort of articulate ways that like, aren't written down in some sort of, process sheet or step-by-step guide that you can just like, pick up and take with you. An example, of this is my background is in the construction industry, but a lot of that was spent working with this particular system called precast concrete, which is actually kind of like it's basically a factory produced material. What you have is like, you make these like big concrete shapes in a factory, and then you drive these concrete shapes to the job site, and then you crane them into place basically, and that becomes the structure of your building.
Is that like the core of prefab? Like, is that really the sort of the heart of what prefab is about, or?
Not really. I mean, not quite, because this is just like, this is a way that you can make like a concrete structure of a building. But it's not, in principle, it's not really any different than like a steel mill that makes like steel beams that then get like taken from the job site. It's sort of a low level-ish prefabricated component. And then if, you bring these things together, and then you still have to do all the other building systems, your windows and your insulation and your mechanical systems, your electrical systems and all that. So it's really a way to kind of get the structure of the building up. And really only certain types of buildings use precast concrete. Parking garages is historically a very, very popular way of building those is with precast concrete. But anyway, so I worked, a lot of my experience is working in construction, but a lot of it was like in this sort of factory operation of these precast concrete plants. And so at one time I was working at this, I had just joined this like new precast concrete company, and they were a company from the Midwest. They were operated out, their headquarters was in Wisconsin, and they had just bought, it set up a new factory in Georgia, which is where I lived. And they were trying to like sort of get this factory online. And so I was like the engineer for this plant, and they spent like years trying to like get this production operation to the point where they could produce as well as their like existing factories in Wisconsin. And they sort of sent people from Wisconsin down to this plant. They sent people from the Georgia plant up to Wisconsin to sort of train them and like, transfer this knowledge. And it just never could quite produce at the level of quality that the sort of original plants that could operate it on. They had, talking again about yield, they had like quite low yield. They were like having to throw away quite a lot of pieces. For some specific products, they had like extremely, extremely low yield. They just never figured out a way to sort of, make these things in the way that they need to be made. And just so much of the knowledge was this, and how to operate these machines and what you have to do to the forms, and like, how the sort of different weather conditions would affect things, and all these sort of little, ways of like making the operation. It just was very, very hard to sort of extract that from like the existing system, which is like, part of it was like written down, but part of it was just like, yeah, in the heads of these workers, sort of embedded in these processes that may be like explicitly defined. This is sort of like grown over time, sort of evolved. And it proved very hard to sort of extract all that and like put it down into a new, and they ended up having just like close this new factory. They were able to never quite make it successful. But you kind of see this more broadly where, sort of, the method of, production method, exists in sort of the organizational procedures, which may sort of not be like explicit, exist in the heads of these workers. And this is very hard to sort of extract all that and bring it to sort of a new location. And so historically, what you kind of see is like, you just need to have like, to get some new operation online, you need to sort of like have the sort of new guys just spend lots and lots of time with these like people who already know how to do it, and just sort of eventually are able to sort of get that to sort of knowledge to sort of transfer, but it takes a very, very long time to do. I've written not in the book, but on the newsletter that I write about like China and their manufacturing, and this is sort of a playbook that China has done for like a long time, which is they want to sort of get some manufacturing and technological capability, and then sort of they entice some existing, Western and Japanese manufacturer to sort of come over there and set up operation. And then they just like will like study it very, very closely and eventually learn how to sort of, do the same thing as well. But it takes a very, very long time. And sometimes it has proved like extremely, extremely difficult to sort of transfer these capabilities. So like, China right now is dominating electric vehicle manufacturing. But before that, they had spent years and years and years trying to sort of build up their, internal combustion vehicle manufacturing. And while today, China is like extremely competitive in like EV manufacturing, and like they're exporting these things around the world, they were never really able to produce an internationally competitive internal combustion, brand. Basically, it just is, it just had a very, very hard time transferring these manufacturing capabilities. So yeah, it can just be very, very difficult to sort of transfer these things to new places. Just the tacit knowledge and sort of, these sort of black boxes are hard.
Yeah, and this is something that Patrick McGee, who was a guest on my other podcast, has written about and popularized big time with his Apple in China, right? This whole idea of how tacit knowledge gets transferred as far as manufacturing processes are concerned. I also had Mark Hyink, who's written about ASML and their UV lithography. And it's the same thing, like very often one thinks, it's this, it's these scientists in labs building this super crazy machine. But the more you understand how ASML operates, you realize that the goal, their chief tech, their Martin van Brink, who just retired, like their kind of, chief technology officer who sort of led the growth and expansion of the company, he insisted on having a basic working machine out on the field, because he said the real development of the machine happens once it's churning out wafers nonstop. So that's it's really fascinating, because you think you kind of produce a really precise, they do 2-3 nanometer work, and you would think, okay, you probably want to perfect the machine before you put it on the factory. It's actually the other way around. You have a basic working machine, you put it on the factory, and the perfecting happens on the ground in the factory during production. And that's tacit knowledge, right? It's that specific factory with those specifications, with the challenges and all of that. And that's extremely localized and tacit. And it's not something that you can just copy paste or scale the way, you would scale software, for example. And I found that super fascinating. Your thoughts on this idea of like, how can we make tacit, like, is there a way to speed this up? And this is especially relevant given the policy challenges, right? That countries that want to either industrialize. So I'm saying like, China plus one policy, you have, India, Vietnam, Mexico, other countries who are trying to woo manufacturers. But more importantly, also in the West, right? Like there's some nearshoring that Europe wants to do as a continent. The US is very openly, I think, trying to bring back manufacturing and reindustrialize. Like, based on your research and understanding, like, what are the real bottlenecks and challenges as far as this transfer or creation of tacit knowledge is concerned? And have you identified any levers, any key things to keep in mind to speed this up or to make it easier?
Yeah, that's a good question. I haven't dived super deep into this. This would be a good project for somebody if, me or somebody else. It's just, better understand, the specific contours of like what this tacit knowledge looks like. Cause like there's different, again, talking about my strategy of like trying to like take some like big amorphous thing and break it down into sort of like specific, categorized chunks and sort of reason about how those chunks operate. You can, I think there's like different like types of like tacit knowledge, right? Some of it is like things like, specific muscle movements, right? Or like specific physical skills that are like just difficult, not easy to describe. Things like riding a bike, right? When you're on a bike and you're balancing on it, it's very hard to like say exactly what it is that you're doing in a way that is like helpful to someone else that is like trying to learn how to ride a bike, right? There's just not like a path to get like the, from your individual muscle movements through words into somebody else's head to their muscle movements, right? It's just it doesn't, there's not a good way of doing that. I have a very young daughter who's like 3.5, who is like trying to sort of, not riding an actual bike, but riding like a big wheel with pedals on it, and like trying to explain to her like how she needs to like push on these pedals to like make the bike go. It's very, very hard to do in a way that like is sensible. You just kind of have to like basically let her just figure it out, which she eventually did. So that's like one type of tacit knowledge, right? These like physical muscle based skills that are just not easy to sort of describe. But then there's just, you can also think of it as just like things that somebody knows and could be articulated, but just nobody has like bothered to sort of do it, either because like they're specifically keeping the knowledge secret, or nobody has like figured out a way to sort of try to elicit it from these people, or something like that. So I think there's like different categories of tacit knowledge, and like the different, and some of it like is more amenable to extraction by deliberate effort than other things. And that's, so I think this, it would be a worthwhile project for someone to sort of dive deep on this and to try to understand like how is this knowledge like in these production processes actually stored, and where are like the load bearing parts of it, and like what form does that exist in. I don't have like an amazing like broad, super deep sense of that, and I think it would be a good good project for someone to tackle.
Yeah, you do have some parts in the book that made me think about this, which was, during the war when they tried to produce, I think it was the B-42, the B-24 bomber in the Ford plants, right? And sort of the documentation standards were completely different. And so, even though you're kind of sort of, transferring the recipe in quotes from one company to the other, or from one plant to the other, they don't know how to act on it, right? So there's a bit of that, what is really knowledge? How do you encapsulate it, and how do you have that common, a common language for people to be able to do this? And I think that there's some good examples in your book, and also the one I think where they were trying to produce guns in the UK, like American guns in the UK. And then, so you see this between countries too, when people are trying to produce stuff. But yeah, it would definitely make, I think, for a fascinating project. And I think I'd love to read that if someone does that. To sort of move on, I think there's one core thing I really want to sort of, dive deeper into with you, because it's something that I wrestle with a lot. And to quote from your book, complex manufactured goods exist in enormous multidimensional landscapes with an effectively infinite number of possible ways of producing them, right? End quote. And when thinking about manufactured goods, I broadly sort of see two prominent business models. I mean, the one is like a one-time transfer, like an ownership transfer of a physical good by a one-time sale. So, all kinds of consumer goods, usually smaller stuff basically, but, where you kind of mass produce the thing and then you kind of sell the thing. And the other thing that comes to mind as far as also production in its broadest sense is concerned is basically, project contracting and delivery kind of work, like architecture, engineering, construction, so anything had to do with bigger buildings or more complex kind of machines, like, if we take one of those ASML machines or like aircraft, like it's not just you produce and you sell it and then it's over. Like there is a whole load of maintenance of, how you operate that thing. And so the whole load of that goes in. And do you see it that way, or like how do you map the spectrum on which these things are? And I think the way you go about sort of improving these is probably also, structurally different, right?
Yeah. So I guess kind of the way that I think about it is like similar to what you said, is that you have like sort of products, which are like, physical widgets or physical pieces of goods that like can do some specific thing. And then on the other hand, you have services, which is like some sort of work continuously provided by like a person or a piece of software or whatever. And the things that have kind of become inexpensive, gotten cheaper over the time, are when you can sort of encapsulate some specific need into a specific product. So you can like sort of your cars or like your antibiotics or your computers or something, need that you're providing gets like incorporated into like this like sort of physical good that you can sort of produce in sort of like an efficient production operation. And the things that are services, the things that require some sort of ongoing labor component, are the things that tend to have not gotten cheap, tend to be more expensive. And one sort of aspect of the construction industry is that despite that you're sort of delivering this like physical good, that it's like structured much more like a service industry. Where you're sort of coordinating with a person who's like, into sort of fulfill your specific needs. And there's sort of an ongoing thing where you're kind of like constantly working with them. And a big part of like why a lot of services are structured as services is because there's sort of the sort of task is like needs to be like adapted to sort of a specific person, or there's like a high degree of like variability and like fluctuation to the extent that like you need something with like the capability of like adapting on the fly to like some sort of specific set of circumstances. And that sort of like flexibility and adaptation requires basically like a person or something with like intelligence to kind of do. And if you can sort of eliminate a lot of that variability or sort of make something a little bit more uniform, it's often easier to sort of encapsulate those things in products and then make those products, in some sort of manufacturing operation that can be quite cheap. So I think a big opportunity, especially going forward with like, as artificial intelligence gets much better and things like that, is sort of taking these things that like historically were like services and historically were like quite expensive because they had this sort of like expert intervention in there that needed to like adapt whatever it is that was done to like whatever specific set of customer circumstances that you have, and being able to sort of start to encapsulate those things and things that look more like products, because now you have some sort of a physical device that can like do the intelligence portion of it, because it can sort of now handle this flexibility in a way that it couldn't before. And so, I'm kind of being a little bit abstract here, but sort of an example of this is like a self-driving car, right? Which now you have, historically it took like a person to sort of, drive you from point A to point B, right? Because, a person, you needed that sort of capability to sort of adapt flexibly to sort of the conditions of the road. You couldn't incorporate that in sort of like an automatic system. But now the sort of self-driving cars are getting good enough where you do have this sort of automatic system that can adapt flexibly to the conditions of the road and drive you from point A to point B without usually a person getting involved at all. So I sort of think that we're going to start seeing these things that historically were like delivered as like services and required like, a sort of high touch operation with like a sort of an expensive expert being able to like deliver it a little bit cheaper, because now you have sort of a sort of intelligence that doesn't rely on sort of expensive expertise, labor to sort of deliver those solutions.
Yeah, and another thing that comes to mind was Dustin Schaefer from Henderson Engineers on the show. And he was speaking about how in these very complex sort of project delivery contracting sort of structures or businesses, you can try to modularize it in a way where you really focus on your proprietary knowledge. And then you can, so you try to then trade components. So basically, if someone's got a big contracting project, but there is a certain module that you can deliver better because you just, that's your proprietary strengths. You have the systems, the algorithms to do that. You can kind of, you can sort of take that out from them, offer that to them, and then you keep, so you specialize on these specific modules in a proprietary way, and that allows you then to win in your market. So it's almost like it's some kind of risk arbitrage, right, for these modules. So I found that quite interesting. To wrap up, the final question, I referenced Charlie Munger's talk at USC Business School in 1994, where he speaks about how, when Berkshire Hathaway owned textile mills and there was a new mill that came about that was, that was able to produce 2x more. One of the managers came in running, mad excited, and told Warren Buffett, "Hey, we need to buy these mills as soon as possible, and this is amazing." And Buffett's reaction was, "Okay, if that's the case, first let's check if it's true. But if that's the case, then we're out of this business because." There are two kind of people that are going to make money out of this. One is upfront, the maker of the machines, right? Because they're selling those machines to the whole market. And so they're definitely going to cash in and sort of, take their slice of the profits. And the other thing is eventually the consumers, right? Because even as demand might grow, but as supply dramatically increases, prices will drop. And so as a textile manufacturer per se, you're sort of being commoditized even more. And so even though you produce more, you don't capture that value. So what are your thoughts on this idea of not just producing more and reducing prices, which is great for consumers, but as a business, how do you stay viable and capture at least enough of the value that you create?
Yeah, I think that's a very difficult question. And I think the way I sort of think about it is that in terms of like, we talked earlier about like the importance of like technological progress and making stuff more efficient. And having like technological progress relies on people like being able to take the time and effort and risk to sort of develop these new technologies and they're only going to do that if there's like a reasonable probability that they're going to sort of that investment is going to pay off, right? They're going to be able to make this thing and this new widget, this new machine, and they're going to be able to like sort of make stuff more efficient and be able to like draw, get returns on sort of that investment. And if you can't, if these sort of if the sort of returns aren't worth it, if like the sort of the it's just they're not going to be able to sort of make the money off it because stuff is going to like the profits are going to be driven to zero or whatever, you're going to have a hard time incentivizing sort of the development of this new technology. And so I think that is like quite important. This is in the sense of like how do you sort of set up incentives such that like people are willing to kind of make the investments in like these new better processes, even if it's like ultimately gonna result in sort of like a race to the bottom and like stuff being commodified and profits just getting whittled away. I don't have like an amazingly strong answer to that. Historically, I think, on the technology side, government intervention has historically been like quite important. Is government, footing a lot of the risk in the sort of initial development of these things. But I don't have an amazingly strong answer for it, but I agree that it is like quite important and, bears thinking about.
Yeah, brilliant. Thank you so much, Brian. It was really a pleasure having you on the show. And you've written really an outstanding book. I would have held it up, but I read it as an ebook on Kindle. But the book is The Origins of Efficiency. This was Brian Potter. Thank you so much.
Thank you for having me.
If you enjoyed this conversation, make sure to subscribe on slasog.substack.com and on YouTube or wherever you get your audio podcasts. See you on the next episode.